So Rich Weiss, I've had the pleasure of knowing Rich for a number of years, and Rich has been absolutely instrumental in getting the Alaska Center for Energy and Power up and running, and to the level of research that we're doing today. Rich, I hate to put this on you, but you're our senior researcher with with the center, and I think we're the same age. So I don't know what that says. So, but you're such a wonderful asset to us, to the state of Alaska. You put so much heart into this, and thank you so much for agreeing to wrap it up tonight with some, I think, the very important information and important topics. So thank you, Rich.
Okay, thank you. Good. Hello. I want to talk to you tonight about, is it up there? Oh, it's there, great. I want to talk to you tonight about the battle for wind integration and heat in Alaska rural villages. And this is a great talk, as Gwen said, to follow up Dave, because these are the sorts of complex systems that we're talking about. All right, in an Alaska rural village, this is a typical electrical grid and a typical heating system. So what you see up here is you see a diesel generator house, basically a power plant. You see wind turbine generators, you see some solar PV, and you see oil stoves for heat. And so this tells us something. The numbers, so we have over 200 Alaska villages that have diesel electric generation. We have most heating, as was indicated earlier, comes from oil stoves. But we have very little wind generation and solar PV in these villages. It is increasing, but so that tells us something. We have a reliance on fuel. And so what do we do about this? So we have two things, or two needs that we really are going after here. One is this idea that we have reliable and cost-effective energy in these remote communities, and that we are able to integrate the renewable resources in an effective way. And this, like we said earlier, goes right to the fact of these complex systems that Dave was discussing. Excuse me, the other thing is affordable space heating. We have to have a way to provide heat for these communities in such a way that the residents can afford it. What are the challenges? And this kind of leads into more of the technical background and where we come in as researchers, but we like to take data. And it's very difficult to take information from these communities simply because there's not the resource there. There's no real good data collection system. The internet is not at the level that it is, say, even here in Fairbanks. The other part of this is what happens when we integrate a system like a wind system. Well, it's highly variable. It's dependent on the wind. When does the wind normally blow? In the evenings, or like say 5, 6 o'clock to maybe 8 or 9 o'clock headed towards midnight. Also the remoteness and the cold climatic conditions that we have. The other problems are maintenance and operation. You heard earlier that Daisy was talking about solar PV, photovoltaics. Well, there's low maintenance there, but in the wind turbine, what do you have? You have the possibility of icing on the blades in the winter. You have maintenance dealing with like the bearings and such inside the motor, the machinery. So those are issues. But really what I want to point out is that heat is important. And that's why I have heat in red here. Heat is very important in these communities. And it just so happens to be the largest percentage use of fuel on average in these communities is heat, for heat. What are our goals as UAF researchers? What are we doing? What we're doing is we're investigating the technology challenges or the technical challenges that exist in these systems, and how can we do a better job of integrating the renewables or integrating other forms of energy that are less dependent on fuel and fossil fuels. We also want to research, test, and develop technologies. And so that's kind of where I'll talk about a little bit of our lab, where we're able to do that. So why not just stick with diesel? Good question, right? Why not just keep running on diesel? Well, if you see in this picture up here, you actually see a picture of a pump in a village, community. Now, yes, this is regular unleaded and not diesel fuel, but the prices are pretty comparable. You see $7.25 for a gallon of regular unleaded. And so these are typical costs for heating oil in communities. You see $7 to $10 a gallon. Well, the electricity cost for bulk diesel to drive in these power plants, these diesel power plants, comes out to anywhere between $30 and $1.10 per kilowatt hour. Now in Fairbanks, we pay somewhere in the neighborhood of what, 20 to 25 cents a kilowatt hour, because it's so dependent on fuel prices. Now that fuel is down, the cost has dropped. So we have an issue here of expense. What are some of the other issues? Well, as you can see here, how do we get the fuel to the communities? If the most expensive is if we have to fly it in. Or you may remember in Nome a few years ago where they actually had to bring in a Coast Guard cutter in order to drive a path through the ice to get into Nome to deliver fuel. And then they still had a mile-long pipeline to get into the community. Well, here's an example of where you're trucking fuel over an ice road, and because the ice is actually a complex system, and you end up having waves of ice, you ended up falling through the ice. Here, you have a barge in southwest Alaska this summer that's grounded, low tide. They had to wait for like 2 days for the tide to come up high enough to where they could continue on to the next community to deliver the fuel. I mentioned earlier about this idea of what percentages of fuel are used in the community for different purposes. As you can see here, 50% is used in space heating. This is sort of an average pie chart for a bunch of communities within Alaska. You can see electricity takes up about 30%, while transportation takes up about 20%. So what should we be concentrating on? Well, does that say dismiss electricity and let's not play with displacing diesel fuel for electricity? No. What it's saying is the largest piece of the pie might be some good low-hanging fruit to look at. This is my most complex graph. What this is it's showing a basic typical load profile for a community. And so the reason for showing this is to say, well, okay, here's my demand. That's this line here. And so what do I have to do? I have to meet that, right? I have to provide reliable power to the community. Well, the problem when doing that, when you integrate other resources, is how do you integrate that so that it's not only reliable, but that it's also effective? And so part of this here is we see the area here where we can do everything with diesel, electric generation. Then our wind starts to kick up later in the day, and we can supply power with wind and diesel. Well, what happens if our wind exceeds our demand in the community? Well, then we can actually have all this excess wind that we have to get rid of. We have to put it somewhere. And so what are the ways in which we can put that wind? Well, the way that we typically do it, or the way that it's done in a lot of communities is not shown here, but it's this diesel idea of grabbing the hot water from the diesel, the cooling loop, and taking it into the community in large buildings. But we have to explore some other methods because we're generating electricity, right? We're generating electricity here from the wind. So how do we do this? Well, one way that we've looked at is to feed, and Senator Murkowski mentioned this earlier in the night, is to take wind, excess wind, and put it into these masonry stoves, where you can have one of these stoves that's about the size of a oil stove that's sitting in each residence. So these are like room heaters. And you have two types of control with these. You have the ability to set the thermostat. You also have the ability to use these maybe more. And that's what we're doing as researchers, is we're looking to say, oh, hey, maybe I can use these to dampen the wind when I have excess wind or I have a big spike in wind. And so yes, I have a more complex graph here, but I also have an illustration. And the idea here is what happens if I'm driving out here. Well, of course, the roads are all icy mess right now. But if I'm driving here in Fairbanks, what happens? I get a lot of permafrost. That was another topic tonight. And what does permafrost normally do to roads? Well, it melts. I get heaves in the road, right? Well, what happens to my truck if I have a bad suspension, or my car? Or maybe it was the bus you rode on, the shuttle bus. I have a bumpy road. I have a poor suspension. That results in a bouncy ride, and in this case, the driver has a headache, literally, and I end up maybe losing my load or getting in an accident. Well, in a wind system, what happens, we integrate wind, we get a wind spike in a system. What happens is we get a wind spike, we get a frequency increase. When I go plug something into the wall over there, I'm expecting an even 60 cycles per second, or 60 hertz. So what we're doing here is we're looking at, okay, are there ways to make that better, to make it more stable, so that the customer gets reliable power. This is the lab. This is the Power Systems Integration Laboratory at the Alaska Center for Energy and Power. This is located at the Energy Technology Facility. And so this is the inside. You can see some of the different pieces and parts here. I'll show on the next slide. This is more of a global picture. So the pieces are, we have a diesel electric generator. We have a wind turbine simulator. Of course, I can't stick a huge bladed machine inside of a building. We have an inverter and a battery bank, and that allows us to get power into the grid like we would from a storage system like a battery bank. And we also have a village load simulator. So this is like what you find in the village. And so the whole purpose for us as researchers is to be able to have a place where we can test this stuff, where we can actually look at these things. I'm running out of time. This is what we're looking at here. We're looking at generator, diesel generator, electric thermal storage, wind turbine simulator, and village loads. So that's the piece that we're specifically looking at. It's not that we're not looking at these other pieces, but we've had concentration on that particular part of the system. Boy, her alarm works. This is the same thing I showed earlier, but here you have an increase in wind, here you have a decrease in wind. So you have to worry about both. When you have large spikes in wind or large deficits in wind. Same thing actually applies to solar photovoltaics. You have a cloud come over, same sorts of things happen. Now, what are the takeaways? I didn't beat your timer, but what are the takeaways? So the takeaways are that we do have the potential for using excess wind for heat, as one example, by storing it. The other takeaway is that there are challenges. There's grid stability challenges. And so what are we going to do with that? Well, that's what we're doing as researchers. And lastly, the real thing I'd like you to take away from this is that we need to, as researchers, be able to find better ways and to develop remote energy technologies to continue the future sustainability of these communities, these Alaska rural villages. And if we don't, they may cease to exist. Thank you.